Hello, happy December 14th. Today I want to talk a little bit about the history of the accelerators which have been based at CERN. So I don't want to go too far into the past. I want to start around the time that we have the superproton synchrotron and the UA1 and UA2 experiments. This was in the early 1980s, and around that time what we knew about the world was there were three generations of matter. We had most of the quarks and most of the leptons discovered. We're still waiting for the top quark. And we had evidence of the W and the Z, but we hadn't actually produced them in the lab yet. We hadn't definitively shown that they were there. And so in the early 1980s, so two experiments were developed called the Underground Area 1 and Underground Area 2, or UA1, UA2, and their purpose was to discover the W and Z bosons, as well as making many other measurements as well. And so what they did was develop the superproton synchrotron, and this accelerated the protons up to 450 gigaelectron volts for each beam. So we have protons, antiprotons colliding head-on at 900 gigaelectron volts. And this actually produced the bosons they were looking for. It produced the W boson, and then later on the Z boson. And for this, the Nobel Prize was awarded very quickly. It's very unusual in particle physics to get a Nobel Prize so quickly. Now, people at the time were already thinking decades ahead. They were thinking, what's going to happen after we've discovered the W and the Z? We want to make a new particle accelerator, and they called it the Large Electron Positron Collider, or LEP. And this was made in the 1990s and operated in the 1990s and 2000s, and this made precision measurements at the Z mass. Now this tunnel was made with another experiment, another accelerator in mind later on. And that was the LHC, the Large Hadron Collider. They recycled the most expensive part, which was the tunnel, 27 kilometers around, to make the Large Hadron Collider. And the advantage of the Hadron Collider is it can go to much higher energies than the LEP ever could. Now, people are still thinking ahead. They're saying, what's going to happen after the Large Hadron Collider? What's going to happen once we've discovered the Higgs boson, once we've either observed or placed limits on things like SUSY, leptoquarks, gravitons, extra dimensions, W prime, Z prime, all these other particles, what is going to happen? They're thinking ahead to the linear collider. So it could be the Tevor scale linear collider, TLC, or CLIC. These are both being investigated and developed at the moment. And they're also thinking ahead to the high luminosity or high energy Hadron Collider, the Super LHC. And so this is part of what we've got to keep in mind when we discuss particle physics. We've got to think decades into the future. It takes that long to develop the technology, to get the funding, to actually build the machines and to get started. We've got to think about 20 or 30 years in the future. And so the LHC is not going to be the final word in particle physics. We're going to have a lot more happening, and that for me is so exciting. It's the kind of thing that really excites my mind. The very long scale, the sort of slow burn physics, where you've got to think ahead and how you're going to shape policy, how you're going to make these machines, and how you're going to get them, so that in 20 and 30 years time we still have a robust and fruitful physics program. It's all well and good having discoveries here and now. I want to make sure we still have discoveries in the future. So I'll leave some links in the description of the video, so feel free to click on those to learn a bit more about the history of the accelerators at CERN and where we'll be going in the future. And I'll see you tomorrow.